Section 2.3 is about polynomial division. Before we get into how to do that, I want to just talk about why it's important and how it's related to what we've been doing so far. I've got up here a polynomial p of x, which is x cubed minus 7x minus 6. And I've written that in factored form, x minus 3 times x plus 2 times x plus 1. Okay. Now, here I didn't show you how I got that. Okay, I just gave you that that is the factored form. But we've certainly seen how the factored form can be useful. And factoring something is essentially like unmultiplying. Okay? This is what I would get if I multiplied this out. The factored form is what I get if I unmultiply. Well, division is the opposite of multiplication. So division is also unmultiplying. Okay? And so division is inherently linked to factors. Here, I could say that x minus 3 is a factor of p of x. And what that means is that x minus 3 divides evenly. That is, with no remainder into p of x. And the factoring is incredibly useful. We've seen if we want to solve a polynomial equation. If we're able to set the polynomial equal to 0, then when we write it in factored form, saying p of x equals 0 is equivalent to saying that the product of these three things is 0. One of them must be 0. So we set each individually equal to 0 and solve. And each of these individually is very easy to work with. That would give us the zeros of our polynomial. If we're graphing, that's incredibly useful, because that gives us the location of the x-intercepts. And the x-intercepts are the only places where the graph could possibly cross the x-axis. So the x-intercepts divide the polynomial into subintervals along the x-axis where it's consistently either positive or negative. So very, very useful in solving equations and in graphing. Okay. All right, so it's because division is so linked to this factoring process that we want to take a look at it. And I basically have three ways that I could write division. If I wanted to look at p of x divided by x minus 3, which we're saying is a factor, I could write it as x cubed minus 7x minus 6 divided by x minus 3. That's certainly a division problem. That's not going to be very useful for working with, but it's a perfectly legitimate way of writing things. I could also write it as x cubed minus 7x minus 6 divided by x minus 3. A fraction is just a division problem. And then I've got another way that I could write it. I could write it as a long division problem. So I could say it's x cubed minus 7x, oops, I'm going to leave some space, minus 7x, minus 6, divided by x minus 3. I left a little space here. I'll come back and address that in a moment. This is the way we tend to write a long division problem here in the United States. Some of you, I know, learned division in a different country, and you probably learned a slightly different algorithm, and you learned a slightly different way of notating the long division. You might, instead of writing your division sign this way, write it more like so. Okay, that's totally fine. It's a perfectly legitimate algorithm for dividing, and it can be generalized to polynomial division. What I'm going to do in this video is I'm going to just remind us how to do long division of polynomials. I'm going to start by going through the division algorithm with just numbers. Okay. For some of you, that's going to be review. For some of you, that's going to be a different way of notating long division problems. Okay. And then we'll try to generalize that to these polynomials right here. As I do that, if you are one of the students who learned a different notational system for division and you're more comfortable with that, totally fine. And if you need my help figuring out how it generalizes to polynomials, set up a time and we can definitely work through that. Okay, but I'm going to be using in these videos, I'm going to be using the standard algorithm for division that's taught here in the States. Okay, so let's see. I want to just review the way long division works with numbers first. Okay. So if I had 4,326 and I wanted to divide by 21. Okay. So these are 4,326 isn't huge, but it's kind of a big number. I don't want to work with the whole thing at once. So I generally just work with the first digit or the first couple of digits. So I might look here. Say, how many times does 21 go into 43? I say, oh, well, that's going to go in twice. So I'll put a 2 up here. I'll put it above this last digit that I was looking at right here. Okay, because essentially this is 4,300, and right now I put that 2 in the hundredths place. 21 would go into 4,300, not 2 times, but 200 times. And that's putting that in the hundreds place for my answer, because I'm going to have hundreds, tens, and then ones. Okay, once I've done that, I multiply. 2 times 21 is going to give me 42. And then we subtract. 3 minus 2 is 1. 4 minus 4 is 0. And then we bring down the next digit. So I'd bring down the 2. And now I'd repeat that process. So I'd say, how many times does 21 go into 12? Well, it doesn't. It goes in 0 times. So then I bring down the next digit. And how many times does 21 go into 126? And it looks like that's going to go in 6 times. So we get 126. That actually worked out perfectly so that we have a remainder of 0. So in this case, 21 was a factor of 4,326. It divided in evenly. That's what we're going to expect to get here, because we've seen that x minus 3 is a factor here. Let me just revise the problem real quickly. I'll just change it to 4,327 divided by 21. I want to remind you of how we deal with remainders if we get them. So this problem would start the same way. 21 goes into 43 twice. That's 42. Subtract and get 1. Bring down the 2. It goes in 0 times. Bring down the next digit. Now, this is going to go in 6 times. That's 126. But now it didn't divide in evenly. We would say that 1 is the remainder. Now, when you first learn division, well, first of all, you're only given things that divide in evenly. And then one day, you're given a problem where it doesn't divide in evenly. And you're like, whoa, it doesn't work. And then you're taught that that's called the remainder. Okay. And you've got several ways of dealing with the remainder. When you start out, you just say, that is the remainder. So we would write 206, remainder 1. And then we get a little bit more sophisticated. So you learn that you could put a decimal here and add some zeros and keep going and get a decimal answer. Or your other option is that you could switch to fractions. So you could just put that remainder over what you were dividing by. And we would say 21 goes into 4,327, 206, and 1/21st times. Okay. So that would be my answer. And this way of dealing with remainders is what we're going to generalize with our polynomial division. Okay, so let's try that here. So first of all, I want to point out that in setting this up, I wrote both polynomials on the inside and on the outside. I wrote them in descending order. So I started with the biggest power, then the next biggest, etc., etc. Now, when I was writing this, I left a space there. That's because I don't have any x squareds. The next biggest power would be x squared. I don't have any of them. I put a space there because just because I don't have any in the initial problem doesn't mean that I'm not going to encounter some x squareds when I'm working this out. Basically, this is going to be my workspace, and I'm going to line up any x cubed with the x cubed. This gives me a place to put any x squareds that I get. This gives me a place to put any x's, and this is where I'll put my numbers. So, at the very least, if you're missing a power, leave a space. I actually like to write in that I've got 0 copies of x squared? I do. I don't have any x squareds. That's another way of saying it. That's just sort of pointing out I have none. And that forces me to leave a space. Up to you whether you choose to write this or not, but I'd encourage you to try it because we're going to be developing a shortcut for certain types of division called synthetic division, where writing in a 0 is going to be necessary. All right, so if I generalize this, I say I don't know how to do this whole problem all at once. I'm going to just look at the lead terms. And that's why it was important that I wrote things in descending order. That's sort of analogous to here. I don't get to just scramble the digits and have a 4, a 3, a 2, and a 7 in any order. The 4 is written first because that's in the thousands place. So that's 4 of the biggest sort of thing I have. That's 4 thousands as opposed to that 2. That's just 2 tens. Okay. So I'm going to look at my lead terms and I'm going to say how many times does x go into x cubed? And another way of phrasing that would be what would I multiply x by to get x cubed? And I can see I'd multiply by x squared. Now I'm going to write that up here. Doesn't really matter where I put it up here. I like to line it up with my other x squareds because down here in my workspace I'm going to need to line up like terms. Not necessary up here, but might as well just be consistent. Once I've done that, now I need to multiply. And now I'm not just looking at the lead term, I'm multiplying x squared by this whole thing. So it would be x squared times x gives me x cubed. X squared times negative 3 gives me negative 3x squared. Notice I got some x squareds even though I didn't have any in the original problem. So now I want to subtract, but I'm subtracting this whole thing. Remember, when we subtract something with multiple terms, we've got to distribute that negative. So I think of subtracting as change the sign and add. Changing the sign is distributing the negative, and then I can combine like terms. Now the x cubes are going to cancel, and that should always happen. We set it up so that we had a perfect match in our first term so that they cancel out. Now I had nothing, but I'm adding 3x squared. That gives me 3x squared. And just like over here, we brought down the next term, I'm going to bring down the next term. There's my minus 7x. And then we repeat. So I look at the lead terms. What would I multiply x by to get 3x squared? 3x. So I'm going to add 3x to the list of things that I'm multiplying by. Very important that I write that plus sign, because if I just wrote x squared 3x, it would look like multiplication. So make sure that if it's a positive thing that you're multiplying by, you do write in that plus sign, because up here we're just adding together all of the things we're going to multiply by x minus 3. So now we multiply. 3x times x gives me 3x squared. That's a perfect match. 3x times negative 3 gives me a negative 9x. Time to subtract. That means we're going to change the sign and add. Now I'm using a different color as I change the sign. When I've just got one color, if I'm just working with a pencil, I'll usually circle the new sign so that I don't get confused about what's what. Okay. All right, the x squareds cancel each other out. Negative 7x plus 9x is going to be 2x, and I bring down my next digit. Then we repeat. What would I multiply x by to get 2x? 2. So I'm going to add 2 to the list of things I'm multiplying by. 2 times x gives me 2x. 2 times negative 3 gives me a minus 6. The whole thing is a perfect match. So when I change the sign and add, I get 0. That confirms what we knew. X minus 3 was a factor. So it should divide evenly into p of x. So it should have a remainder of 0, and it did. And if you look, x squared plus 3x plus 2, that's exactly this. So anytime you've got a division problem, there's a corresponding multiplication problem. So if p of x divided by x minus 3 is equal to this polynomial, that's equivalent to saying that this polynomial times x minus 3 is equal to p of x, which is what we have right there.